Hello everyone, welcome to the channel Learn Math with Shobita. Today I am back with some questions from linear algebra. First question, let W1 and W2 be two subspaces of a finite dimensional vector space V, and let dimension of W1 plus dimension of W2 greater than dimension of V. Then option A, W1 intersection W2 equal to 0, singleton set 0. W1 intersection W2 not equal to singleton set 0. Option C, W1 intersection W2 empty. Option D, W1 union W2 is V. Let us solve the question. We have dimension formula, dimension of W1 plus dimension of W2 is equal to dimension of W1 intersection W2 plus dimension of W1 plus W2. So rearranging the formula, dimension of W1 intersection W2 is equal to dimension of W1 plus W2, dimension of W2 minus dimension of W1 plus W2. We know that W1 plus W2 is a subspace of V containing W1 union W2. Therefore, W1 union W2 equal to V is not possible. So, option D is false. Okay. Further, dimension of W1 plus W2 is less than or equal to the dimension of V because W1 plus W2 is a subspace of V. So now dimension of W1 intersection W2 plus dimension of W1 plus W2 is greater than dimension of V because dimension of W1 plus dimension of W2 is greater than dimension of V we have given. Okay, now dimension of W1 intersection W2 is greater than dimension of V minus dimension of W1 plus W2, which is greater than or equal to 0. This is because this. Okay, therefore dimension of W1 intersection W2 is greater than 0. This implies W1 intersection W2 contains a vector other than 0 vector. Therefore, W1 intersection W2 is not equal to 0. Hence, option B is true. Next question. Let T from R3 to R2 and S from R2 to R3 be two linear transformations. Then which of the following is true? Option A, S composition T is not injective. Option B, S composition T is injective. S composition T is surjective. Option C, option D, S composition T is bijective. Given T from R3 to R2 and S from R2 to R3, then S composition T is a mapping from R3 to R3. Since the dimension of domain is R3 is greater than the dimension of codomain, T is not injective. So let us give explanation for this. According to rank nullity theorem, nullity of T plus rank of T is equal to dimension of R3, which is equal to 3. Rank of T is less than or equal to 2 because here the codomain of T is R2 and the range is subspace of codomain. So rank is nothing but dimension of range of T. So dimension of range of T is less than or equal to 2. This implies minus rank T greater than or equal to minus 2. Therefore, nullity of T we get greater than or equal to 1. That is, kernel of T is not equal to 0. This implies T is not 1, 1. Then there exist two vectors v1 not equal to v2 such that T of v1 is equal to T of v2. That is, S composition T of v1 equal to S composition T of v2 with v1 not equal to v2. This implies S composition T is not injective. Therefore, option A is true. S composition T is not injective. Consider the following statements. Statement 1. The 0 vector cannot be a vector in basis of R5. Statement 2. There are 4 linearly independent vectors in R to the power 5. Statement 3. There are 7 vectors in R to the power 5 which generate R to the power 5. Which of the statements are true and which of the statements are false? So statement 1. This is true because we know that basis is a linearly independent set. Also, if 0 vector belongs to any subset S of V, then that set S is linearly dependent. Therefore, the 0 vector cannot be an element in the basis. That is, 0 vector cannot be a vector in the basis. If 0 vector is in the basis, then basis should be linearly dependent, which is a contradiction. Okay, so statement 1 is true. Then let us see what about statement 2. Any subset of linearly independent set is linearly independent. So here R to the power 5 has dimension 5. Therefore, it has a linearly independent set of containing 5 elements. And any subset of this set having 4 elements is also linearly independent. Therefore, there are 4 linearly independent vectors in R5. This statement is true. Third statement, there are 7 vectors in R5 which generate R5. This statement is also true. If a finite set S spans a vector space V, then dimension of V is less than or equal to cardinality of S. So here dimension of R5 is 5. So it can, there should be a set spanning the R5 having 7 elements. And another, that is, in other words, superset of a spanning set spans V. Hence, there are 7 vectors in R5 which generates R5. So, all the 3 statements are true here. Next question. Suppose T from R2 to R is a linear transformation such that the kernel of T is x minus x, x belongs to R. If T takes 1, 0 to 1, then T takes 1, 1 to which number? Okay. Given T is a linear transformation from R square to R. Okay. Kernel is, what do you mean by kernel? Kernel of T is nothing but set of all x in R2 such that T of x equal to 0. So here it is of the form x comma minus x. So T of 1 comma minus 1 is 0. Also they have given T of 1 comma 0 is 1. We have to find T of 1 1. We can write 1 0 minus 1 minus 1. You will get 0 comma 1. Now applying linear transformation on both sides. Since T is linear, we can apply here T of 1 0 minus T of 1 minus 1 equal to T of 0 1. So 1 minus 0 you will get T of 0 comma 1. Therefore T of 0 comma 1 is equal to 1. Now 1 comma 1 can be written as 1 0 plus 0 1. Applying linear transformation on both sides, T of 1 1 equal to T of 1 0 plus T of 0 1, 1 plus 1 which is equal to 2. Therefore T of 1 1 is equal to 2. Thank you friends. Please share and subscribe the channel.